Gurjeet Singh holds a technology degree from Delhi University, a PhD in computational mathematics at Stanford. And since his graduate school days, he has been developing key mathematical and machine learning algorithms for topological data analysis, his subject he's talking about us tonight. He later worked at Google, at Texas Instruments, before co-founding the company Ayazdi. And he's here tonight to talk to us about data today and into the future. Please join me in giving a big round of applause to our speaker, Gurjeet Singh.
Thank you. Can everybody hear me? All right, good deal. So mic check. All right. So the title of the talk is The Shape of Data and the Things to Come. I am going to be talking about using topological data analysis to understand large, complicated data sets and what it means and why it's important. And you'll see in a couple minutes here why the word shape is important. I'm going to be saying that word a whole lot in the talk. Before I do that, a quick introduction. This picture is actually a very good introduction to my career overall. I had graduated in the year 2008 with my PhD in computational maths. Really wanted to go be a scientist somewhere, and Wired magazine came out with this magazine cover, in May of 2008, saying it's the end of science, and that was really disheartening because that was a thing I wanted to do. But the interesting idea behind this was the following. Around the year 2000 or so, DARPA and NSF, who fund a lot of scientific research here in the US, realized that the way people were doing science had changed pretty fundamentally. They realized that we were all of a sudden in a mode where we would create data first and ask questions later. One good example of this phenomena was the Human Genome Project, in which we collectively invested many billions of dollars, collected the first 7 human genomes in digital form. And we didn't really know exactly what science would come out of it. Lots and lots of great science came out of it, but we didn't quite know exactly what would come out of it. And the way we got science out of that project was essentially by having collected the data and then looking into it. And so DARPA and NSF realized that all of a sudden our ability to collect data was outstripping our ability to ask interesting questions of the data. And so they started investing in fundamental maths. Their blue sky idea back in the year 2000 was that computers keep getting cheaper. There must be a way in which we can build hardware and software systems that will allow scientists to do more science from the data. So the idea behind this Wired story was, now all of a sudden we will have access to algorithms which will be able to sift through data and sort of get us more science than we might otherwise have gotten. So the idea kind of made sense. And the way we approached it, since we were one of the groups that they funded at Stanford to do this science, was we used a very old area of math called topology, which I'll explain in a minute here, to essentially look through very many large number of disciplines and find new interesting findings in them. We published in areas as diverse as protein folding and cancer research and image compression and econometrics. And so DARPA basically gently asked us to commercialize our research, and that's why we started the company Ayazdi. And that's pretty much all I'll say about Ayazdi. So for the rest of the talk, here are the 4 things I want to do. I want to talk about, introduce the notion of topology and topological data analysis. I then want to give you a bunch of real-life examples of what is possible with this technology. Then I want to basically take this talk into this idea of explainability in AI. I believe that a lot of our lives today are run by algorithmic systems that most people don't really understand. Even the creators don't really quite understand. And I believe that topological data analysis is a good way for us to get a handle on explainability of AI algorithms, even when the algorithms themselves are opaque to the technique. And then finally, I just want to talk about the future of what you could do with what could happen with topological data analysis and with topology at large. So that's what I'm going to do, OK? So the first thing is I want to motivate an idea in machine learning today, which is called unsupervised machine learning. And that will allow me to introduce the idea of topology to you. So let's think about how we learn from data today. Imagine that you work at a lab, maybe you're a genomics researcher and you're collecting gene expression data from a bunch of cancer patients. Or maybe you are at a bank and you have to construct a stress test model. You're being given a large Excel file, and then you have to learn some stuff from that data. The way it works today is you start with a smart person. And typically, this is a smart person who's stayed in university, maybe done a master's or PhD, unlike maybe a Zuckerberg or a Bill Gates who dropped out. So this is a person who stayed in school. This smart person comes up with questions or guesses or hypotheses, right? So they might say, okay, maybe this is a question in the data that I might go ask. They can then convert it into code of some sort, and I'm using the term code very liberally here. I don't mean any specific technology. Or they could use what's known as business intelligence software colloquially, where you can use the user interface to pose questions for you. You run those against a database, see the results back, and then maybe you're right, maybe you aren't. And in general, in the software industry, we've paid a lot of attention on those two bits on the right, the databases and the BI systems. We've tried to make databases bigger, faster, and cheaper so that the cost of asking a question can be as low as possible. And the second thing that we've done from a software perspective is we've tried to democratize access to data. So we have great business intelligence software today that relatively easily allows you to ask questions of complicated data sets. Even Excel is a very good piece of software to allow you to do that. And this has been a great advance. One of the major problems in this method overall is that it's a guess and verify method. You have to hazard a guess, and then the software allows you to verify whether your guess was correct or not. And the issue with that is that in the past when data was simpler, making guesses was something that we could do. Today, making guesses is something that's pretty much entirely out of the domain of people when the data is more complicated. And in fact, in this process, with complicated data, the only time you learn something is when you hazard a guess, and the software comes back and tells you that there is no support for your guess, that you learned nothing. Then you know that your guess was incorrect. If there is some support for your hypothesis, you don't really know whether your hypothesis was complete or not. So the completeness of your questions is actually a huge problem. And you wouldn't know. So that is kind of the motivation of an area of machine learning called unsupervised machine learning, where you expose large complicated data sets to a machine learning system, and the machine learning system learns something about it and helps you understand it. And this also allows me to very quickly introduce this notion of topology to you. So now I'm going to ask one math question. So I'm warning everybody about that. So to introduce a math question, this is a map of the city of Königsberg. It's now in Russia. And there's a river that runs through this city. It's the name of the river is Pregel, River Pregel. And the way the city is set up is that there is an island in the middle. The river kind of flows around the island, and then it forks into two pieces, right? So in the year 1700, or thereabouts, 1730 actually, there wasn't a whole lot going on. So people were generally looking for interesting dinner conversations. One interesting dinner conversation was, could you go through the entirety of the city of Königsberg, having crossed every bridge only once? Okay? So that was a dinner conversation. Again, without making any statements about people's lives back then, that's what they had going on. And it was actually a vexing problem. People for about a decade or so tried to get to an answer to this problem, and they couldn't. Okay, so here's the math question. How might you, and I'll take three guesses, how might you attempt to answer this question? What would you do? Three guesses. Graph theory, good. So some background there. That's great. Back then, people didn't know graph theory, right? So, sorry? Permutation combination, okay. That's also a good answer. What else might you do? Trial and error, great, perfect. And in fact, that's what people did almost all the time. One of the things that people tried was they basically said, let me measure the length of each bridge. let me see what is the exact kind of the coastline, and let me try and figure out how long will I have to travel. Right? All of these things that were geographical in nature that you could very easily see from a map, people started measuring those things. And they couldn't solve it. It took about a decade or so, and there was a the most famous mathematician, arguably, Leonard Euler, who eventually solved this problem. And what he realized that there was a lot of extraneous detail in this problem. Right? The length of the bridges doesn't really matter. Right? He realized that lots and lots of these things were kind of irrelevant to actually solving this problem. So he realized that the thing that matters is that there are these 4 land masses that are colored in various colors here, and they're connected to each other via these bridges. And so, as you suggested, he basically turned it into a graph problem. He said, here's a graph, and A, B, C, and D are the 4 land masses, and the lines between A, B, C, and D represent the bridges that connect the various land masses. And very simply, he realized that there are 3 edges that connect every node. And so what that means is that if you have to cross every bridge only once, then there has to be an even number of edges, 2 edges in particular. And so since there are 3 edges to every node, it is simply impossible for somebody to actually cross every bridge only once while traversing the city. So this was a key insight, and he then started developing the area of topology and graph theory and the study thereof. And the key thing about topology is that it's a study of holes, and I'll describe that in a couple minutes here as well. So that was his key realization, that whenever you're trying to study a problem, try and throw away a lot of the extraneous detail and try to reduce the problem to sort of the essential detail in it while maintaining the essential complexity. So let me take the example a little further now to modern times when we actually have more data sets, and let me give you some intuition behind topology. Here are these, on the screen I have these 4 shapes, and I'll give you a quick story about each one of these shapes very quickly, and then I'll explain an aspect of machine learning behind these shapes. The first shape is very simply a line. So for example, imagine depressingly somewhat, if you're trying to buy a house in the Bay Area, and you make a plot of the price of the house versus the square footage, you will see a linear relationship. And in machine learning, this is called a regression problem, where imagine if somebody said, I want you to predict the house price, I'll give you the square footage. You might draw a line through the set of points that you've collected, and that might give you some sense for how much you'll end up paying for the house. And obviously, you'll decide you can't pay for it. But nonetheless, that's the process you'll go through. So I want to give you some insight into how does this machine learning process work. What does regression do? Regression assumes that your data looks like a line or a plane, and then it tries to find the best line or plane that looks like your data. Okay, so keep that verbiage in mind. Another common problem that we solve in many different contexts in business or in science is called clustering, where you're given a bunch of data, and you're trying to determine, are there self-similar parts of the data? So for example, if you've collected data about, let's say, a lot of patients who have diabetes, type 2 diabetes, let's say, you might want to know, are all type 2 diabetes patients similar, or are there multiple types of type 2 diabetes patients? So you might attempt to solve it via a clustering problem. And the way clustering works is, again, very similar to regression in that you assume that your data breaks up into multiple pieces, and then you try and find the best decomposition of your data into that many number of pieces. Right? So similar to regression, you assume a particular shape, and then you try and look for that shape in your data. The third example is a loop. Imagine that you are an economist, and for every year you figure out the interest rate of the Fed and the growth rate of the economy. And these are your 2 axes, and you put a dot for every year that you collect the data. You will notice that the data evolves in these cyclic patterns, where when the interest rates are low, economies grow, and then eventually when the economies have grown too much, the interest rates are tightened and the economies start to shrink again. Again, we are in topsy-turvy world these days, so no bearing to real world these days, apparently. But nonetheless, that's what you would see in your data. I'll come back to that picture in a second. Look at the 4th picture. Imagine that you're, let's say, flying from San Francisco to New York, and you stick 2 sensors on the plane. You measure the amount of lift that the plane is experiencing versus the drag that the plane is experiencing. And when you plot the picture on the screen, you'll see a picture like this fourth picture on the screen here, which is that for the most of the flight, you will be in the middle part of the region where lift and drag change a little, but not a whole lot. But there's a few anomalous things that happen. You take off at some point, you land at some point, and you might go into turbulence and come back at some point. And those are the three flares that you see here. Okay. Now with this background, I want to make 2 points. The first point is that the shape of the data actually contains a lot of information about it. If you knew the shape of the data, you wouldn't have to ask many questions about it going in. The second is we have great algorithms called regression and clustering that solve the first 2 problems, but we don't have an algorithm called loop detect or flare detect. And in fact, the category of shapes that you actually see exhibited in real data sets is so vast that it's kind of pointless to come up with a prototypical shape first and then look for the shape in the data. And so that is kind of the motivation behind using topology to understand the shape of the data, because the shape of the data is meaningful. Everybody with me thus far? Yeah? All right then. So for people, I'll go through this slide very quickly. This is for people who might be slightly more technical in the machine learning space. But I just wanted to give you a sense of sort of how this interacts with machine learning or how it's dependent on machine learning. So what you see in this picture, there are 3 data sets. Every row represents a data set. So the first data set are these kind of 2 clasping points. Half the points are blue and the other half are red. The shape in the middle has blue points in the middle, and then there's the circle of red points that envelopes that. And then the third shape is basically 2 clusters, red points here and blue points here, kind of like politics, I guess. So, and what you see in every column thereafter is a particular machine learning algorithm trying to discriminate between the blue points and the red points. Okay? So you see the decision surface of these machine learning algorithms. The exact names of these algorithms aren't important, so don't worry about those. What's important here is that you can see 2 things. The first thing is that data has shape, as you can see immediately in this toy example. The second thing you can also see is that every algorithm also has a shape. So for example, if you look at the second column, which is the first colored sort of picture with the bands, you will notice that no matter what the shape of the data is, the algorithm always has this linear structure where it will find a line and then it will discriminate away from it. If you look at the second from the last column, you will see that this algorithm has a shape which is that it wants to discriminate data into boxes. So it wants to find axis-aligned boxes that have various opacities. And so the key realization here is that data has shape and algorithms also have shape, the algorithms that we use currently in machine learning. So it is really important for us, if we're going to have a hope to understand what's going on in these algorithms and how they make decisions, it's really important for us to understand how these 2 things are linked together, how the algorithms work together with the shape of the data, and when will they make errors, and what kind of errors will they make. Everybody with me thus far? So just quick summary, and then I'll switch into examples, which will be a lot more fun. Topological data analysis is basically a formalization using this old area of math called topology that allows us to study shape of data, shape of algorithms, shape of decision surfaces. For people who are slightly more technical in the audience, it allows us to merge together the results of various other algorithms in a coherent way that you can learn from it together. And the final point that's the most interesting point is that it's a compressed representation. It compresses the data. And compression is really important, because when people talk about big data sets and how vast it is, big data sets are actually kind of useless. You want data sets that are as small as possible. You want to eliminate complexity that's meaningless, right? So if you go back to the thing that I said about the map, there's a lot of complexity in that map. The exact shape of the coast is kind of irrelevant. So there are many, many details in data that are irrelevant. and it's actually very useful to understand the essential complexity of the data. So compression is a very key part of all sorts of machine learning, and in particular, topological data analysis is kind of based on outputting a compressed representation. And it also happens to be visualizable, which is sort of very, very, very useful. Okay, make sense? All right, let's move on to examples. So the way I'm doing these examples is I'm basically picking 3 examples from biology, because I think most people can relate to it in a lot more easily. And then I'll one very quick slide give you sort of a couple of examples in other domains, like in financial services and banks and so on. Okay, so the first example, this is in type 2 diabetes. So this was done in collaboration with Mount Sinai in New York, with the Dudley lab. And what they did is that they ran a very interesting experiment. They went to 10,000 people who had type 2 diabetes, and they collected data from the 10,000 people, which was their clinical record data and also their genetic data. The particular type of genetic data that they collected here is called single nucleotide polymorphisms. So imagine an Excel spreadsheet where every row is a patient, and there are 1 million columns where you're basically probing their genome in 1 million places, and you're noting the alphabet that you find in those particular 1 million places. And then you also have about 100 or so columns, which are their clinical information. So things like their weight, their BMI, do they have retinopathy, do they have liver disease, do they have kidney disease, things like that. And now, obviously, as you're imagining this Excel spreadsheet, you have 1 million and a few hundred columns, and you want to study this data. Of course, you can't ask questions anymore, because it doesn't make sense to say, is it the case that people who have a polymorphism in position number 6, 79, and 51 also have retinopathy? Right? These questions are meaningless. There's just way too many of these questions that you might end up asking. So they ran the data through this topological data analysis system, and it created a map visually that looks like this image behind me. And they discovered that there's actually 3 distinct types of type 2 diabetes that are genetically distinct. And one of them was basically called the type 2 diabetes complication category, people who had high BMI and diabetic retinopathy. The second type was potentially caused due to cancer. And the third was the most common type, which is the subtype 3, which is typical of heart disease and metabolic syndrome. Now, the key point here is that they discovered all of this using the software, but we are now in an age where the world's best scientists need this kind of software to learn from and analyze their data. It is no longer feasible to ask questions one after the other and expect to find interesting things in your data. The second example is from breast cancer. It's actually one of my favorite data sets to talk about. This was one of the papers I published during my PhD. And the reason why it's one of my favorite data sets to talk about is it's a very old data set. This was the first data set ever collected about the gene expression of breast cancer tumors. So this was collected by the Karolinska Institute, and it's called the NKI data set. And for every tumor that they excised, they measured the activity of 23,000 genes. And for every one of those patients and tumor samples, they also measured some clinical variables. So, for example, did they survive 5 years out? Did the cancer metastasize? Did they have to have a mastectomy or a lymphectomy, and so on? And the data set, by the time it came to me, had been studied to death. We threw it into the software, and we saw this Y shape. And in this Y shape, from a network perspective, the structure is that every little node contains a group of patients who are similar to each other across all of their genetic data, not the clinical data. And 2 nodes are connected if they share some patients. And in the software, you could color it by various things. So for example, in this case, I've colored it by the probability of mortality 5 years out. Red means almost certain bad prognosis for those patients. Blue means that there is a higher probability they'll survive 5 years out. Now, in breast cancer literature, one of the things that's very well known and understood and well studied is the behavior of a particular gene or a particular hormone called estrogen receptor. When the estrogen receptor levels are high it's generally the prognosis is generally not great. And so what happened in this software is as soon as we put the data into the software, we discovered this Y structure. We colored by mortality. And we saw this group of patients, which are circled here, who had high estrogen receptor levels, but they all survived. And it's a relatively small part of the data. It's maybe only about 5% of the patients. But we replicated it across many, many different data sets, and we're always able to find this signature. And now there is actually a test that you can do for it, and sort of there's a differential procedure that's prescribed to these patients. So that's the reason why it's one of my favorite data sets to talk about. But it's also an example of why the shape of the data illuminated this thing that otherwise would have gone unnoticed. All right. Third example, this is done in collaboration with the Schneider lab at Stanford. And so David Schneider, he's asking a very interesting question. He's basically looking at one patient at a time, and he's trying to see the arc of a disease. So for example, somebody gets malaria, and for the entirety of their stay at the hospital, he'll collect their blood samples and measures their proteome in the blood. Proteome essentially measures a bunch of proteins in the blood. And the question he wants to answer is, what is the disease trajectory? In what cases does the disease trajectory go into a bad state? In what cases does the disease trajectory come back into a healthy state? Now, from a topological perspective, one thing you'll notice is that all of the examples I'm showing you here are full loops. And so what that tells us is that all these patients started from a healthy state and came back to a healthy state. So that's why it's a full loop. There are also examples in his paper where they could predict sort of some offshoots of the circle where people did not return to healthy states. And so this was actually really insightful for them to actually place a patient in a part of the loop and say, I believe that you are 60% through the cycle. So for the first time, we can actually give a measure to the percentage completion of the disease, and whether you are actually going to recover, or if you're not going to recover, then maybe the protocol needs to change, or maybe you have a secondary infection that you need to get treated for. And so that was really insightful. Make sense? All right. So now I'll switch gears and I'll talk about some examples out of biology. So the first example is from financial services. One of the major pain points in our current economic system is money laundering, where we lose billions upon billions of dollars every year to money that's been laundered and has been converted into illegal money. Now, banks suffer the brunt of this, which means that banks are almost being asked by regulators to become law enforcement. So banks are supposed to monitor every transaction. And if they feel that a transaction is suspicious, not only are they supposed to stop the transaction itself, they are supposed to report it to the regulators within 72 hours. And so it's a hugely expensive process for the banks. An average bank, such as an HSBC or a JP Morgan, spends about close to $700 million a year in this compliance process. And now, the statistics of the process are also very complicated. So what happens is you have a team of investigators, oftentimes anywhere from 5 to 10,000 people who are investigating these transactions. And 99% of the times, their investigations do not result in a suspicious activity report. So 99% of the work of 5,000 people, you very well might not have done and achieved the same risk to the bank. So this application essentially utilizes a behavior profile of customers. What it says is that I'm going to study every customer based on the transactions that I've seen from that customer over the past year and a half or 2 years. And based on that, I'm going to assign a risk to every customer. And based on the risk classification of the customer, I'm going to either investigate at a higher level or lower level. This system basically reduces their investigative volume by about 26%, while ensuring that nothing that was suspicious in the past stops being suspicious and discovering new types of money laundering that they would have missed otherwise. So that's the first example. The second example is in clinical variation management. Our healthcare system in the US is not amazing. And so there are many side effects of this. One side effect is that if you go to a hospital system and, let's say you are there for a knee surgery, and you go to the hospital system and say, okay, how much is it going to cost? How long am I going to be here? They basically can't answer these questions in any level of detail that a smart person or a regular person these days would like. And the question is why? Why is it the case? Why can't they just find these numbers? Why is it difficult? The problem is that there is next to no standardization in healthcare. Now, some of it is expected. Everybody is unique, so you can't have a cookie cutter sort of procedure for everybody. But the amount of standardization in our healthcare is so low that every patient is actually treated uniquely. So what this application does is that it hooks into their electronic medical record systems, and it hooks into their financial systems, the hospital's financial systems, and it tries to determine the good variation in care that's being offered to patients for every procedure and the bad variation that's being offered to patients for every procedure. And it helps physicians look at that data, helps them understand the data, and helps them discover and adopt best practices. And again, this is a category where, for example, if you go for a knee surgery, the number of events that happen to you are close to 5,000. And these are all the way from nursing orders to dietary orders to the actual implant to the post-op procedure to the follow-ups and so on. But the variation is humongous. So the 5,000 events that happen to me or that might happen to somebody else are so different that it's actually a very, very difficult problem to find the some standardization in sort of how the care will progress. The anecdote here is that one of the latest people to try this is a small community hospital system in Florida called Flagler, who basically determined that for patients suffering with pneumonia, and they have an aging population that they serve there. For the patients suffering with pneumonia, they were able to lower their length of stay in the hospital by about a day and lower the cost of per patient per encounter by $1,000, which at their scale is worth millions of dollars, and obviously it delivers better care to many of those patients. Third example, cybersecurity. Again, not a day goes by when you don't read a report in the Wall Street Journal, something about a hack or something of that sort. Our general response to cybersecurity in the tech industry has been firewalls, which is to say we are going to stop bad people from coming into the network. But once somebody is in the network, it's actually relatively hard for somebody to figure out how they get in and what should we do now. So what this application does is that it does a novel form of anomaly detection, where it tries to detect when an internal employee is being impersonated by an external actor. And so in its first application at a large telecom company, essentially helped them discover 15 criminals who were already hiding in their system from amongst 11.5 million accounts. And finding 15 out of an 11.5 million of anything is generally a hard thing to do. Final example, stress testing. This is also in financial services. So after the 2008 financial crisis, which was obviously a very difficult and bad event, the Fed essentially mandated that every bank or every fiduciary institution which carries cash accounts has to predict what will happen to their accounts in the event of a downturn. How will the cash react, and will they have enough to cover their reserves? Do they have enough cash to carry the risks that they are carrying on their books? One particular bank, Citibank, kind of failed this process 3 years in a row. Their then CEO got fired, because of this process. New CEO came in, also failed once, so that didn't help clearly in that case. Now the question is, why do they keep? Why is it that they are not able to do this? What was the problem? They have all the data. It's all internal. They have a few hundred people building these models, so it's not a lack of people. They have all the software that mankind has ever created to solve this problem. And they have the will to solve it. It's not lost on them that their market cap just sort of dropped by $13 billion when they lost when they were not able to pass the test. It turns out that the problem is actually finding the right hypotheses, actually figuring out which are the key variables that affect your business that you can stand behind and that you can convince the regulator you understand your business well. And so again, this application helps these banks get through this stress test process way more dramatically than they might have otherwise. Make sense? All right. So let me shift gears and talk about explainability. The reason I'm passionate about explainability is because as a creator of these kinds of AI systems, um, you know, there is a responsibility that we have in sort of figuring out when they might go wrong. A lot of our lives today are governed by these narrow AI systems that already work quite well in the narrow domain in which they are built. But how do we govern them? And I think that's an important problem for our age that we need to try and solve. So I believe there are these 5 interesting questions that we have to begin to answer, which is the input data biased? So if the input to a machine learning system is biased, or if it's incorrect, or if it has a blind spot in a certain area, how do we detect it and how do we fix it? The second is the model making systematic errors? So is it the case that whenever it's raining outside, the model is just showing me weird news on Google News? Again, that doesn't happen, but that's the kind of thing you would like to know. How certain are we about the model in the regime of the input data? So I have a model, for example, a mortgage model at a bank, and it's making decisions, but a new type of lender has started applying for my model, maybe because there's an economic shift or a social shift. Is the old model is not valid anymore? How do I know that it's actually making good calls or not? Can you explain the logic behind the model? So generally the answer is no. But then what can you do? What's the next best thing you can do? And how do we detect regimes where we're missing data, and then how do we gather it? So let me give you a few examples of these problems. The first one is the input data biased. This is a generally pretty depressing study. The data is available on CDC. And so what this data is, for every hospital visit, when somebody goes into triage in the ER, there is a model that's run to figure out how acute is this. Should we look at it right away, or can they wait? And so that's called the triage model. And what you see is on top, the same network or the same data, it's colored by the predicted mortality of the model. And at the bottom, it's colored by the actual mortality that you see. So you will see a couple of things in this. The first thing that you can see is that generally speaking, the model does a fine enough job, right? Generally speaking, you see more bad mortality towards the right. Generally, the model is making those predictions. It's fine. The second thing that you will notice is that the model is very optimistic, right? The model is very regular and very optimistic. There are lots of places here that are certainly at the bottom yellowish that the model is, yeah, it's blue, it's happy, it's fine. The one particular area that I want to point out is circled up here, which is the model says it's totally fine, no problem, and those people all end up basically not surviving the ER experience. So the question is why? It turned out that these people were delirious enough that they couldn't answer a few questions on the survey. So missing data was causing this problem in the model, right? So this is an example of how do we detect bias in the input data to the models, where we can then go hopefully correct it either in some human way or process or in some systematic way. Second example is the model making systematic errors. This is an example from a fighter jet. If you've read the news recently, the F-30 and F-16 programs aren't doing amazingly well. And one of the major reasons is that a lot of pilots in these systems are having hypoxia events. And what that means is when they're flying the plane, all of a sudden they become unconscious. And when they eventually land, it turns out that they had a severe lack of oxygen for a small amount of time, that led them to becoming unconscious. Now, obviously, this is not lost on anybody, not on Lockheed, not on Boeing, not on the Air Force itself. So the question is, what are they doing about it? And to their credit, they've installed lots and lots and lots of sensors in the plane. So in fact, a plane today collects about a terabyte of data every minute from all these sensors, right? Now, again, the obvious problem when you collect a lot of data is how do you know when do you know that data is actually pointing to something useful or not? And similar to the compliance thing that I talked about earlier, in this case, 99% of those cases are just false alerts. They are alerts that happen where you alert on every single variable. So for example, the thrust of the plane is I'm making this up, but the thrust of the plane is too high. So you're alerting on it. But it's not really meaningful. The things that lead to these weird events are combinations of events that you have to find. So in this example, you discover the systematic errors that the false alarm model is making, and then you expose it to through a user experience that's usable by a domain expert, so that a domain expert, who wants to get to the root cause, is able to figure out the root cause and fix the problem at root cause. And so this is an example in figuring out systematic errors. The third is how certain are we about the model in the input regime of the data. So we've created a model. And so this case, this is a financial stress test model. And we want to figure out which variables are the most important. I'm just speeding up a little bit just looking at the time here. So I'll go quickly through this. But again, the case here is that for every time you get an input to the model, you can place it on the model that you created in the backend, this topological map, and you can figure out is it a region of high certainty or not. So at least you can attach estimates to every prediction that you make individually and say that, hey, if I'm recommending this news article to somebody, what is my estimate that I will be correct in this prediction? So I think it's a really important ability for models to have to do that. Finally, the second last example here is how do we explain the logic behind the model. So this is a picture of Alvin. For people in the machine learning community, this was the first time we built kind of a self-driving machine. And it worked pretty well, actually, right? It worked amazingly well for the time. It had a camera system and a self-drive system and all of that. It turned out that, they built this over the fall. They built it really, really quickly. And when they tested it on the first day of summer, it didn't work. So the question was why? Why is it not working? And it turned out that the model had learned to basically see the sky as being gray. So if the sky was blue, the model was like, what just happened? I don't know what to do anymore. So today, in our image detection systems, we run way more complicated models. So this is a deep learning model. For people who've seen the news recently, deep learning is making all sorts of waves in perception problems, things like image classification, text and sound and so on. And in all these perception problems, when you learn these models, they're essentially huge arrays of numbers. That's what a model is these days, like these deep learning models. And they require a large amount of data to train, and there is no easy explanation. So if somebody said, why did this model do this? What am I going to say? Will I say that the computer knows how to multiply numbers correctly, so hence it must be correct? Because that's the best I can say today, is the model learned these numbers, and the computer knows how to multiply, so that's it. We think there's a better way. So this is an example where you use topological data analysis to introspect into the model. What you do is you take those large weight matrices that you've learned, you throw it into the topological data analysis framework, and it helps you figure out what are the base patterns that the model has learned and how are they connected to each other. In fact, it also allows you to speed up the training. So there's a problem in machine learning called sample efficiency. How much data do you need to train a model so that you like its result? Sample efficiency is a huge problem. And so topological data analysis, at least in this perception visual problem, allows you to speed up your training time by about 4x by giving it some topological information about the base underlying data. Yeah. Finally, how do we, okay, let me skip that. Generally speaking, there are two things about the future that I'd like to say. The first thing is AI systems of the future. What should we expect smart AI systems of the future to do? And I believe these 5 capabilities are fundamentally important. The first is to discover, which is when exposed to large complex data, these AI systems have to be able to come up with hypotheses from the data without a human being telling it exactly what to do. The second is to make predictions. I think we do a pretty good job, and we are continuing to do this better and better. The third is to justify, which is to explain the logic behind the model and why it makes the decision it makes. The fourth is to act, which is that we must build these systems for domain experts. If you're going to require an army of data scientists to do any of this, then the common man has no hope of actually being able to use these effectively. Like I said, even the best scientists in the world, need these kinds of systems today. So it's very important to build contextual user experiences for them. And finally, to learn, which is as data evolves, the models have to understand how they are feeling and evolve. So that's the final bit. Okay, now things to come. Now this is not about topological data analysis, but this is about topology in general and why it's useful and why you should care. The 2016 Nobel Prize was awarded to Thoules, Haldane, and Kosterlitz for topological phases of matter. Essentially, they studied very small films of atoms and molecules at very, very cold temperatures. And there were some interesting quantum effects that nobody had explained before that they were able to explain. And it has led to a huge amount of research in the area of topological materials. Some of the things that we have already benefited from are better hard drives. So for example, the data density on hard disks today is orders of magnitude higher than before because of these kinds of topological discoveries, and we are able to engineer topological domains on the platter itself to increase its capacity. The second is insulators. So there is an interesting topological effect where you can build wires which are super thin, which can conduct charge and insulate at the same time, where the core of the wire can start conducting charge, but the edges of the wire are insulators. So it's a very exotic way of building these things, but these might be commonplace by the time my kids grow up. Superconductors, a lot of the recent research in superconductors has been made possible due to topological properties at the quantum scale. And finally, in computing, there's quantum computing is a new frontier in computing, and one of the major problems in quantum computing is essentially the stability of the bits. So topological properties of quantum materials have a chance of actually being able to make more stable qubits, where we'll be able to read data from them with a higher probability of success than before, just because topologically we can lock the data in, so to speak. All right, that's what I had. Happy to answer questions. I'm sorry I went a little bit over.
So one of my jobs here is to ask the kind of goofy questions somebody else who is also not a math major might also be afraid to ask. So I'm going to do a couple of those in here while you are thinking of your much better questions that you want to ask. And we have somebody on our staff has the mic. So what you're going to want to do if you want to ask a question, get that gentleman's attention. He will hand you the mic, and then we'll call him. So don't worry about letting us know, but look out for the fellow back there. Have a seat. Thank you so much. That was fantastic. So I'm going to ask one of these questions right now that I bet I'm not the only one that's going to. So probably a lot of us in this room, the only version of topology that we are aware of is topological maps. And not thinking very complexly about it, I was like, oh, it shows the height. So can you connect that concept, or is this a correct application of topology? How do we better understand topology through being experts about topological maps?
So topography and topology are different.
Okay.
Topography is sort of.
See, my job. That's my job.
But there is a connection. There is a connection, though.
Good. Thank you.
It actually turns out that that there are certain sorts of topological constructions that require these functions, such as the height function. So in topography, the way we do topography is we have one function, which is the height, and we look at the contours of the height. Wherever the height is stable, we draw a contour. Right? That's how topography works. In topology, you basically extend the idea to many different types of functions. There are limitations on the types of functions, but there are many cases where you can build these kinds of functions. One example of this being useful is the example that I gave about stress testing in banks. That actually uses one such function that we call eccentricity mapping. And it turns out that function, which was developed in biology many years ago, ended up being super useful for understanding these financial kinds of data sets. And nobody would have thought about it.
So in a way, and I'll probably do this wrong too, but it's in a way almost like 2D versus 3D. Is it like it's one dimension? Topography is a single dimension height, and the others are the yes. Okay.
Yeah.
Okay. Fantastic. Thank you. You did very well on that. Yeah. Do make sure to hold your mic.
Yep.
There, so everyone can hear you. And we want to thank, by the way, a quick shout out to our Long Now members who are watching or listening from home. Thanks, guys. We're really glad you're paying attention, and another great reason to join Long Now. So let's go back to the beginning of the history here. What was the German gentleman's name who?
Leonhard Euler.
Okay. Sorry, how do you spell it?
Euler, E-U-L-E-R.
Okay. Now, were there any precedents whatsoever from what was? I mean, is that kind of made out of whole cloth to solve this bridge problem, or is?
Yeah. So
what
he
are the
was,
components of that?
Euler was one of the best mathematicians ever to have existed. So yeah, I think he just made stuff up in general, and it worked out. That's how most great mathematicians have done their work. That's basically the reason why the Fields Medal, which is kind of the Nobel Prize of Mathematics, is typically, earned by very, very young mathematicians. Is you got to make stuff up in general.
And we're going to get to audience questions in a second here, but you touched on it's so interesting, the applications across different industries that have different problems. But I'm curious, in a way, things kind of we can extract data about all these different things, and the data itself, in its form, may look very similar. When you're looking at it with this kind of analysis, do you see sort of similar shapes, as it were, across different areas? Is the health data and the financial data, are there, it's funny, one thing I think about in this area is people that have done like stock price analyses that have different shapes that they respond to in their bidding and so forth, right? So are the insights that are seen in, say, some of this health data around a disease useful in some way, or are there almost archetypes that are applicable to a financial set of data or something?
So I think not exactly, but slightly related is this notion of algorithmic serendipity, which is something that we've noticed over and over and over again. So one of the ways in which we architected our software was to basically say, we have this huge library of machine learning functions, all sorts, supervised, unsupervised, semi-supervised, and so on. And we would basically, from a software perspective, run all of them on as much data as we possibly could for any given problem. And over and over and over again, we've realized algorithms that were developed in one area ended up being useful in another area. And people in, for example, financial services never studied algorithms in biology. And they had no reason to. Their textbooks don't mention them. Yeah. But it turns out that they are this algorithmic serendipity is actually very, very beneficial. It's kind of manna from heaven. You don't have to do anything. You just throw it into the blender, and it comes out and being useful.
I think we have a question from the audience back there. Please.
Hi. Thanks so much for the talk. It was terrific. I'm asking this question from a cognitive science point of view. So I know that you're not trying to model human cognition or human learning, but it does strike me that we know some things about human learning, particularly in the areas of vision and language, that are illustrative and offer some possibilities of improving a merely statistical or stochastic analysis approach to finding things out. So in vision, for example, as you know, we have to solve the inverse problem. We have to compute a three-dimensional representation from a two-dimensional informational array. And the consensus among vision scientists, the consensus is there have to be some kinds of innate constraints on the hypotheses that get considered. There's variation about how they think those hypotheses are embodied in the brain. But it strikes me that some of these issues might be more fruitfully approached. You might get a better learning model if you could somehow incorporate the analog of innate constraints. Is there any interest in doing that sort of incorporation?
Yes, I love that question. Thank you for asking it. So there are two studies that we did at Stanford that I think are illustrative of this. In biology, there are a lot of cognition studies are done on mouse models. So there were two studies that we did in collaboration with UCSF where we had a Utah array, it's called. It's basically you implant it in the brain of a mouse, and then you collect data from their brain while they are doing various tasks. So one study which we did was essentially on the vision tasks, where we were showing them, imagine a black and white screen where you're cycling the black and white. So imagine a black bar that's moving down the screen, right? And we collected that data from the brain of the mouse. And when we analyzed the data, it actually turned out that the topology of those signals replicated the topology of the animation that was running. The animation was running in a loop, right? The bars were moving down and then go up and then move down and then go up and then move down. And you could see in the data that we collected and we analyzed this way that you could see a loop in the data that we collected from the brain signals as well. So in other words, the topology of information representation in the brain mimicked the topology of the information that was being sort of fed into the rat or mouse in this case. The second study we did was on the hippocampus region of similar mice, where they were in a maze. And the question was, could you recover the structure of the maze just purely from the basis of the signals that, from the spikes that you're collecting from their brains? And it turns out that, again, you couldn't construct the details of a maze, but you could construct the topology of the maze. So for example, if the maze had a hole in the middle, you could recover it very easily. But for example, getting a corner was next to impossible because, again, topology doesn't see corners. But the structure of what somebody went through was topologically represented in their brains, and we could recover those signals from the data we collected from their brains. So it's somewhat related. And yeah, I echo the emotion. Yeah.
And I love that question. Also, I had another thought that popped into my head while you were talking, when you were talking about an instance of bad data, and bad data is obviously it's garbage in, garbage out, yeah. Right? And so often it is that risk that you don't know that your input is bad and so forth. So something is a different sort of kind of human comparison that came to mind is, are these models being built in a way with a kind of self-reflective capacity, or a capacity that's sort of going, it's analyzing, I don't know, that's looking for, in what ways are they looking for bad data or looking for other essentially kind of biases or protecting us against biases that we may be prone to doing it? How, and maybe just in general, in terms of its own, or the risk of a built-in, a coded-in bias, if you will, and as well as the human biases of those who are reading it after the fact. Yeah.
So generally, it is somewhat technically possible to do it today.
Mm-hmm. And what would you call that? How would you better characterize what I just mumbled through?
So let's say that you are building a mortgage model. That's a very simple example everybody understands, right? So if you're building a mortgage model to figure out whether to approve somebody's mortgage or not, right?
So essentially that's analyzing someone who's applied for a mortgage as well. Okay.
That's correct. Okay. Now, oftentimes the way those models are built today is that a bank or a lender would look at their data across the history, look at the decisions that their lenders made, right? And then try to mimic that. Okay. Now, the question is, if the lender made a mistake, what do you do about it? Is that bad data? It's not malformed.
Yeah.
It's collected and it's sort of represented in the correct way.
But it's well documented. There have been horrible things that have been happening.
That's right.
With the lending history of banks.
Exactly,
yes.
right?
Yes.
So the question is, that is a kind of bad data problem that you can actually completely solve today.
Interesting.
That is a kind of bad data problem where you can throw it into such an analysis and you can figure out what are the areas where the model is making systematic errors, what are the biases, what is the structure of the data overall, and what is the structure of the decisions overall. That's the kind of error that you can eliminate. There is another kind of error in the bad data category, which is really hard, which is, now imagine let's say the same bank, right? Let's say they were operating in Singapore, and all of a sudden they make a decision to go start operating in India, right? They have great data in Singapore and great socioeconomic structures. In India, they're very different. So when you start applying a similar logic to a completely different ecosystem, it won't work anymore. So now you have data that's, again, well structured and well collected and well formed, but it's useless. And that is slightly harder because it's also a cold start problem. Okay, what do you...
But at a first level, does it tell you it's useless? Is there something in the algorithm, or even just the process of using it, that helps you to understand you've got a problem here? That's one of the other questions, is how can it, in a way, it's kind of drawing a circle to say there's something over here. And it may be something very profitable, very useful that's over here, but it could also be we have a problem in Sector 7 and what do we do about it? So how are these technologies or is this framework good at signaling us for those kinds of, hey, human who has a different kind of look at this, apply attention over here?
It can do it in a well-running system already.
Sorry, in a what?
In a well-running system.
In a well-running
system. So, for
system,
example,
yeah.
if you've been doing it in let's say Singapore again, right, as an example, and you've been doing it and you've been collecting data for how it did, then the model can start suggesting that even though I am trying my best to emulate what a human lender did, but here's what I'm seeing in my error surface, and here's what I suggest you change. That is possible. But if you are in a de novo situation where you don't have any data,
right? So you're saying it's got a baseline. If it's got a baseline, now it's got something to see that variance.
That's right.
Interesting.
But the interesting thing about the baseline is that it's an engineering problem now. In many cases, we can actually engineer the system so that it has and creates a baseline and operates off of that. And taking that engineering approach to these systems is actually, I believe, will be a huge bang for the buck in general in the economy if we applied it.
We have another question on the second row.
Thank you very much for this wonderful talk. The question that I have is about scientific methods of analysis through the history. So there was the age of proof, mathematical and logical, and there is the age of modeling with calculus and all the descendants of it. And then there is the age of ultimate pattern recognition by the machine. So how do these connect? For example, what's the role of something like a stochastic simulation or continuous simulation in this world?
So that was a really great question.
Make sure you're holding.
Thank you. Yep. That was a really great question. So I think if I can, let me summarize the question just so we are on the same page, and then I can answer it if I'm correct. So the question was, we've had many ways of inquiry. We've had sort of prove it to me, write an algebraic proof. We've had the, here's the data and here's the equation, and now does it work or not, right? And the question was, what do we, or how do we deal with stochastic systems where we are simulating and we are collecting data, right? Okay, so I believe that we do stochastic simulations in areas where it's too expensive to do real simulations, right? Either they are too time consuming, or they are too resource intensive, or they won't finish, or it's simply infeasible in the sense that there are just way too many variables, right? And oftentimes when we code these stochastic simulations, in a lot of stochastic simulations, what ends up happening is that you find the structure that you coded into it, right? So for example, if you made an assumption implicitly, explicit assumptions are easier, you can write them down. But if you made an implicit assumption in a stochastic simulation, discovering those becomes a very huge challenge. And in many cases, those implicit assumptions are not desirable. So this is something that happens in economic models all the time, where we make stochastic economic predictions. And stock markets do this a whole lot. Market makers of all sorts do, like BlackRock, they all do this. And in many of these cases, the implicit assumptions really get you. Because explicitly you said, okay, so the interest rate is going to go up. Fine, that's fine, you've written it down. But you never wrote down the fact, or rather, implicitly it was the case in your model that whenever interest rate went down, your economy grew, right? So for example, that stochastic simulation, that might be an implicit assumption, but that's not true in today's cuckoo days. So how would you, discovering those kinds of implicit assumptions is where this would be important.
Right, back here.
So I'm going to ask you to make a subjective assessment of the world here. I was very intrigued by your example with the bridges, that people had a hard time figuring this thing out, and we're doing things like measuring the lengths of the bridges, and I'm even struggling to find out what kind of calculation they were trying to do. When the example that's given is like what I was already thinking in my head, now that I've already absorbed the wisdom of the mathematician, but this problem of people paying a lot of attention to things that are wrong, or having like really dumb theories that aren't even related to the problem they're trying to solve. Don't we still have that in this world? So my question is, I get the thrust of your talk that we have some tools to kind of get around this problem, but are we also swamped by people looking at the wrong information and paying attention to things that don't matter? And if you were to give an assessment of the world in terms of whether we're paying more attention to those things versus better approaches, I'm curious if there are examples that come to your mind or what you would say about that bigger question.
So I think generally it's an untenable question overall, right? Are people focusing on the right things or not? The word right is... Yeah, that's right. So for example, in the case of the city, the right was a verifiable answer. You can verify whether you've crossed all the bridges once or not, and so on. But in many of our real life problems, right is sort of undefined. That said, though, I think there is reason to be optimistic, right? Which is when we look at, for example, a lot of the scientific data, which is sort of where all this research originated, then to a large degree, we actually do have tools today that allow you to take in large amounts of data and then focus in on interesting parts. It is for the domain expert to decide whether they're the right parts or not and whether they fit in with their contextual knowledge. But at least it will focus you on the interesting parts of the data that have some coherent structure to them. But I think at the end of the day, I don't think this is a problem we'll ever solve overall. And we should hope not, right? It would kind of make it useless to exist, like some level of, there is this, since we are here and I see all these science fiction books around here, there was this novel by Arthur C. Clarke, in which there's a perfect society and everything is great and everybody does the same, and so on and so forth. But the people who programmed the perfect society, oh, thank you. The people who programmed the perfect society also programmed a joker in the society who every now and then would just come in and wreak havoc. And shit would hit the ceiling and it would be bad, right? It would be horrible. And eventually at the end of the book, you discover that they allowed this joker system to exist in the novel or in that society just to keep things interesting. Otherwise, it would be too programmatic. So like in some sense, you kind of hope for some whimsy, right? So in some sense, some of it I don't, it's fine. Some of it should exist. But for many of the interesting scientific questions, we actually do have good solutions today.
So, Gurjeet, I want to ask you this question because you have this interesting background and you've cut across a few different worlds that I think you have a unique perspective in that, which is you have a math PhD, you have the computer science, but you've also been an entrepreneur in this frothy Silicon Valley, and in this moment when terms like artificial intelligence and big data, the kind of marketing terms are things that we all know about, but what actually they mean is they're rather representing pretty broad things that you're dealing with the actual technology, let alone the math and theory even behind that to a certain extent. So I'm curious for your thought about, and I guess I think about it in three ways, that there's the business is doing what it's doing and it's communicating in certain ways to tell businesses that something like machine learning and artificial intelligence are useful for their business. We've already talked about the fact that one of the things topological data analysis does is it makes some of these the benefits of this technology accessible when you don't have the data scientist at a certain level on staff, and so in a way it's democratizing and spreading some of these capabilities around. But at the same time, there's this hype machine, and there's a blur on it. And then in a third way, in addition to the people that might be shopping for this technology and the people that are producing this technology, the third is kind of the general public. A lot of us are in where we may not be laying our hands on this, but we're getting a sense of, and we may have a more common sense of what AI means or whatever. So I'm curious what, with the perspective again that you have, having gone through kind of a bunch of different layers of this, what is fact and what is fiction here? How mature is this technology? And also, again, speaking maybe just to the broadest audience as well as to folks that are more closer to this tech today in this audience. What should we know to make sense of what this moment is and what the real benefits are of some of these things?
Yeah, so there's a lot there.
Yeah.
A couple of things. I think you started kind of with the arc of my career.
Yeah.
I think in general, math and computer science, even though they kind of work together, have generally been at odds with each other, in the sense that the area of math somehow has gotten into a state culturally where people who are mathematicians want to do pure math things. They want to stand in front of blackboards and write with chalk. That's, I kid you not, one of the biggest, most heated debates that we had at Stanford in the math department was when they replaced the blackboards with the whiteboards. And thankfully they've gone back, which is the right call. They're black now. That's the way they should be.
Well, watch out for automation. That's
Right.
all I have to say.
But you know, in general, I think math has kind of gone off in a bit of a tangent where generally culturally
That's
speaking,
almost fitting, but yes, go ahead.
pun intended. but I think generally speaking, computer scientists distrust mathematicians to a degree in the sense that because they have to get over a lot of mumbo jumbo that they don't understand.
Yeah.
And mathematicians generally don't want to quote unquote stoop low to communicate their ideas in a more effective way. So I think generally speaking, there is a lot in math which was discovered hundreds of years ago, which is actually super duper relevant, which I hope that fields come together in a more coherent way and sort of benefit each other. I think there's a lot. Like, had we not done the number theory, we would not have had Bitcoin. You could argue about its value. I like it, but you could argue about it. But we would not have had it had we not have researched number theory and cryptographic systems. So I think generally these two fields need to come together in a more coherent way than they are today. Now the second part was to sort of think about what is the hype and what is the reality in AI. I think generally the sad fact in 2019 is the bar to call something AI is very low.
Yeah.
Like you can have an Excel spreadsheet with a few formulas and get a gold star for it being an AI system today. So
Don't try and run a spaceship with it. It's just not going to work. Yeah.
So like in general, whenever somebody says, blah intelligence or blah intelligent or whatever, it's not, it just isn't. In fact, I think we should stop using the word intelligence in the context of machine learning because it is an anthropomorphic idea which sort of leads to pointless debates and pontification, which is useless to people. So I think we should try and divorce ourselves from the idea of intelligence because we have no idea. We have no idea. What we have built thus far, to our credit and to the credit of everybody in this area, is we have built narrow AI systems that are very good at solving specific problems very well and with high repeatability. But in no way, shape, or form are these systems anywhere close to being intelligent in a way that you or I would call them intelligent. So that's what I would say about marketing versus hype. Basically, the one question you need to ask is, do you have software behind this or are you doing it in Excel? And, like nothing bad about the Excel people, they are good people, but it's not AI in general. Nothing is overall, is my view. And we are a long ways away from it. There's a lot we need to know and study.
Okay. All right. Well, I think we're going to have to leave there. We're a little bit over time. You're going to stick around?
Yep, I'm around, and there are some neat animations that are running back there. For people who want some more technical geekery, I'm happy to oblige.
Yeah. So Gurjeet's going to stay here. We'd love for you to stay. Come up. He's happy to chat with you. I know a bunch of you had questions we didn't get to, but thank you so much for being a great audience. Gurjeet, let's have a big round of applause for Gurjeet.
Thank you.